All right, let's get started. Um, so just as an introduction, my name is Shyam Dwaraknath. I am one of the research scientists in the Person Group and one of the organizers for the Materials Project Workshop. I'm sure you've all been bombarded by emails from me just going over the process, various parts of registration, answering questions. And so, we've had a lot of contact via email, but now you'll hear me talk through a lesson today. So I actually saw a question in Slack that I think is a good precursor for this first lesson. And the question effectively is, how much DFT do you really need to know in order to be able to run calculations? And when I started in this group, I guess at this point 4 years ago, you had to understand how to use DFT in order to successfully run a calculation. Thanks to a number of new developments that we've built in automation, you can at this point run DFT calculations without actually understanding how it all works, simply because we have good guardrails in the automation. So you're unlikely when you start off to produce a calculation that is fundamentally flawed. But in order to really leverage and use DFT to the fullest, you should have a good basic understanding of what you can and can't do with DFT and what it is you're computing, as well as a good material science foundation. So while you can run calculations, and I'll go through that process today, if you really want to use DFT in the way that Materials Project does, to compute properties, decide which one's the best, and then make follow-on decisions either in your experimental plan or in a more follow-on computational plan for research, you really should understand what DFT is doing. Now, with that being said, we're going to dive into today where we're going to focus on 3 lessons. Basically, in the automated DFT, we're going to have 3 core concepts. The first concept is basically what does it mean to have inputs and outputs for other codes, and how can you use PyMatGen to actually read and write files for other codes. The second is something that we call input sets, and this is how we standardize parameters for DFT codes. This is the first set of guardrails that I was talking about. And then the final mini core concept is going to be how you actually go through the process of running an automated calculation with our code called Automate. Now, a lot of the work in automating DFT comes in the setup. Each supercomputer is different, each computational environment is different. There's a lot of little configurational parameters that are unique to each system. But once you have those set up, you can basically run high throughput calculations. That means tens, hundreds, thousands, tens of thousands of calculations in a rapid mode using our Automate and Fireworks codes, which provide pre-built recipes and the workflow manager. So why don't we start today? I'll just go over this one more time. If you're logged into CoCalc, you'll start off with a screen that looks something like this. If you want to go into the workshop folder, then into lessons, then 05 automated DFT. This is the folder you should be in if you want to make a new notebook, a blank notebook to start off. I suggest you make it here because we will use some of these other files that are available in order to go through the lesson and the exercises. So I'm going to start off by creating a blank Jupyter notebook. Now, basically I'll let that start up. And we're going to go through how we can use PyMatGen in the beginning, the first 20 minutes, to write and read input and output files for VASP. So PyMatGen actually has a number of different interfaces for a bunch of different DFT codes other than VASP, and some non-DFT codes as well, such as LAMPS, which is molecular dynamics. But for this example, we're going to focus on VASP, which is a density functional theory code that we use in the Materials Project to compute most of what you see on the website in the database. So let's start off by actually importing a structure so we can start playing with that structure. So I'm going to type from PyMatGen import structure. I'm going to run that with a shift enter. It'll take a second to import that. And then I'm going to load an aluminum chrome structure that's already there in the files in this folder. So I'm going to say struct is equal to structure.from_file. I'll open and close my parentheses and open my quotes. Type in AL and press tab. And you can see that I have an autocomplete. It gives me 2 options. I want the CIF file, which is my structure definition. If I shift run this, I will have imported the structure, and I'm just going to print the structure to screen just by typing it in. And I can see this is some structure that has aluminum and chromium in it. It's an aluminum chrome alloy that has a it's a numeration of a random disordered structure. But even though most files that you'll get for structure definitions are CIF, or this crystallographic format, codes such as VASP, quantum espresso, AT, exciting, lamps, they don't take CIF files, they take their own custom format. So the first thing we need to be able to do is actually convert into the format for that specific code. So if I type in from PyMatchN.io, I can hold down Shift and press Tab and take a second. Oh. In fact, let's do it a different way instead. Let's import this. So I did Shift Enter on import PyMatchN.io, and then I can type dir and type in PyMatchN.io. Take a minute to run really quickly as it loads all the modules in there. And you can see there's a bunch of folders that it's already showing, but it's not showing my other modules. So instead, I'm going to delete this and say PyMatchN.io and I'm going to press Tab. And in my dropdown, I can see all the different codes that I have available. These are modules that correspond to a single code. So I have AT, I have exciting, there's a code called Lobster, I have VASP, XChristen, 1A90, but I want to actually focus on VASP. So I'm going to add the from back at the beginning of this, and I'm going to basically import from the inputs module in here a class called the POSCAR. And so if I run Shift Enter, I've imported that module and I can now use it. I'm going to say my underscore POSCAR is equal to POSCAR the class, open and close parentheses. I'm going to give myself a few more cells so that you can see in the center. And if I put my cursor in the center of the parentheses and hold Shift and press Tab, you can see that it shows me the init signature. So this tells me what it takes. It takes a structure. You can have a comment. You can have true names, velocities, and some other things that are specific to how VASP basically takes inputs. So I'm going to close this introspection, and I'm just going to give it the structure. So I'm going to say structure is equal to struct. I'm going to Shift Enter, run that, and then I'm going to print POSCAR, or I'm actually going to print my POSCAR. Close that and run. So this is what a VASP input looks like. It basically has some enumeration where it talks about what the number of elements are. It has the lattice construction, how many of each elements are available, and then basically all the sites enumerated along with a little label that just tells you what this is. Now, we could go ahead and construct this relatively simply for most structures, but if you can already manipulate your structure in PyMatchN, PyMatchN will take care of building this for you, so you don't even need to worry about that. But what if you already have a calculation and you want to figure out what's in it? We can also use the same POSCAR object to actually read a predefined POSCAR file from a calculation we run. So I'm going to say, let's say example underscore POSCAR is equal to POSCAR dot, and let's actually do introspection. So I've got my dot there. I can hold down Shift, press Tab. Nope, that's not what I wanted. I'm going to hold down Tab, and you can see that it's given me a list of various things that I can select. So in this case, I want to read a file. So from file sounds like it's the right kind of method. If I click on from file, I can close the parentheses, and then I can hold Shift and Tab. And now this shows me that in the signature, I can give it a file name. I can tell it to check for the appropriate POSCAR, which I'll go over in a minute. And I can read velocities, which is another flag that you can turn off. So let's close that. And let's actually go to one of the examples. So I'm going to put in quotes. I'm going to put a dot / to reference the current directory. I'm going to hold down, actually, I'm not going to hold down Shift in this case. I'm just going to press Tab. And it gives me the autocomplete for everything within this directory. So I have in this AL16CR10, let's see, where is the, sorry, let's go down to this VASP underscore AL16CR10 underscore example directory. If I click on enter on that, that'll autocomplete that. I can press tab again, and now I can see all the files that are available. And I want to select this poscar.gzip. So you'll notice that this is not a regular poscar file, this is a .gz file. That extension means that this file has been compressed with the gzip algorithm. Now this is a small file, so you're not saving much storage, but some of the files that VASP outputs can be hundreds of megabytes in size, and there's lots of zeros in there. So if you use a compression algorithm like gzip, you can actually reduce the size significantly. One of the nice things about our PyMatchen interface is even if it's a compressed file, we can still read it directly. PyMatchen takes care of uncompressing it on the fly. So you basically can store a lot more information when you're actually saving your calculation and not worry as much about storage. All right, let me increase the font size of my screen. So I'm going to shift enter and run that cell. And you'll notice that there are some warnings. And basically, when we load a file from VASP, we do some extra checks behind the scenes. So one of them that I'll mention is something called a potcar, which is a pseudopotential. So when we run a DFT calculation, we're not simulating every single electron. There's a core set of electrons that we're basically saying just pretend to be like some sort of potential. And there's an extra valence set of electrons that we simulate explicitly using our density functional theory. These are the electrons that contribute to bonding, so those are the ones we really care about. Now, these potcars are actually something that comes with VASP, and normally VASP is a licensed code, so the potcars are part of the license as well, and unfortunately we cannot distribute them as part of the workshop. What we've done is we've basically put in some dummy potcar data so that you can still play around with this example, but then we basically don't expose those licensed pieces of code and data for you. So if you want to use VASP, for instance, you need to get a license and then you can run it on your own system. Or for instance, supercomputers such as Cori have been pre-compiled for basically general use for anyone that has a license. And so these warnings are basically saying, hey, there's something up with those potcars. They don't look right. So maybe you want to check and see what's going on. In this case, for this workshop, this makes perfect sense. So let's print out this example poscar, sorry. So I'm going to say print example underscore poscar, and I'll shift run this. And you can see that it actually has the same kind of structure as before. And basically it's the same structure, and that's why it looks the same. But what if you want the structure from this poscar? You've read it, you can print it, great, but I want to take this into the rest of PyMatchen and do some manipulation. Well, what you might say is poscar.structure, and you can, not poscar, example underscore poscar.structure. And if I shift enter that, I have my PyMatchen structure, and I can go ahead and use this and manipulate this. I can do substitutions, I can make this into slabs, I can add defects. I can basically make a new structure, put that back into VASP using this input output, run my calculation, and get something new in terms of energies or electronic structure. So why don't, at this point, we switch to the exercise? So I'm going to click back on this folder so I can get back into the MP workshop. I'm going to click on exercises. And what we're actually going to do for this exercise is move to a different code. So the structure of IO in PyMatchen is the same for a number of different codes. And while VASP is the most dominant code that we use, because most of the materials project is inorganic crystalline materials, there is a very strong development in the molecular database that we're building. And so the primary code we use for that is called Q-Chem. So for this example, what I would like you to do is actually go through the process of exampling the IO module for Q-Chem. So we're going to start off by importing molecule from PyMatchen. We are going to import an ethylene carbonate molecule and then print it. So I'm going to shift run this, and it'll basically show you, what this molecule looks like. A very simple molecule. But what I would like you to do is figure out what you need to import from, oh, sorry, this is input, the second example. Let's go to the first example. Same thing, we're going to import this ethylene carbonate molecule in the first example. And what I would like you to do is figure out what you need to import in order to input the QC input file that Q-Chem takes. So most of this line is already filled out for you. There's basically something that has a from file. It has a .qchem ethylene carbonate folder in the workshop files. And there's a mol.qn.gzip. Again, this is a gzipped input file already. And I would like you to figure out what class you have to import from this pymatchen.io.qchem.inputs module that will then let you read that and print out the molecule. So let's give ourselves 2 minutes to go through this process. All right, so let's walk through this. So I have from pymatchen.io.qchem.inputs. I'm going to delete this little blank line here. I'm going to press Shift and press Tab. And that should normally show me, so on CoCalc, it's not doing the auto-complete. So what you can also do is you can do an import. And actually, let's make that on a new line. Let's select this one line, press A. And then let's do import pymatchen.io.qchem.inputs. And then in this line, if we do from import, hold down Shift, press Tab. Okay, so the autocomplete is not working right now. If I make a new cell by pressing either A or B, so if I highlight this, if I highlight this and I press B, I can make a new cell. So I'm going to say pymatchen.io.qchem.inputs dot, and then press Tab. It should autocomplete. And if I look through this, I can see there's only a few options, and there's a QC input class, which sounds about right. You'll find that in pymatchen, we try to name things as obvious as possible. In a few situations, they seem a little bit odd, but for the most part, they are named in a way in which they kind of represent what they actually do. So QC input is the class that I actually want. So I'm going to scroll down here and type QC input. So that means I need to put QC input as the class here. So I'm going to type QC input. And if I shift run this, you can see that it loaded this file and it printed out this ethylene carbonate. Okay. So in that same sense, we're going to go a little bit more advanced and we're going to talk about outputs very quickly. Outputs work in the same way with VASP. You can load them exactly the same, or sorry, with pymatchen. There's usually an input and an output module if the DFT code is complex enough. And for Q-Chem, we have this output module, and in that we have an output. Now, unlike VASP, Q-Chem has one primary output, so we can actually just import one or read one single file to get all the Q-Chem outputs. So since the autocomplete is not working in CoCalc, I'm going to highlight the cell right above this bit of code, press B to get a new cell, and in this, I'm going to import this outputs module so I can do autocomplete. I'm going to say import pymatchen.io.qchem.outputs. I'm going to shift run that. And I'm going to highlight the cell in which I would complete and press A to add another cell right above it. Then I can type pymatchen.io.qchem.outputs dot and press tab. And again, the autocomplete shows up. I have a lot more options this time, but again, the classes in pymatchen are named as obvious as possible. So in this situation, it's likely QC output is what we want. So if I click that, it finishes off. I can highlight QC output. I can Control C to copy it. I can highlight those blank lines and press paste to get my QC output. And then I can highlight the blank lines again, get QC output, and actually run this bit. And I'm going to, in the interest of time, move forward to just finishing off this simple exercise for you. There's a QC output. In the QC output, there's actually a data or attribute. and it's a dictionary of all the properties that come from the output. So if I shift enter, run that next file, you can see there's lots of different pieces of data. There's errors, there's warnings, there's the CPU time the calculation actually ran in, there's something called VASP charges, there's the molecule from the last geometry, there's a number of different properties we can get. But if I want to access one of these, since this is a dictionary, I use basically the square brackets to access any one of these keys. So I'm going to, for the purpose of this example, get the optimized geometry. So I see there's this molecule from optimized geometry. So I'm going to highlight that key. I'm going to hold down Command C or Control C if you're on Windows. I can delete this blank line, and then I'm going to paste that entire key with the string quotes around it. And if I shift run it, you can see that I get a new molecule geometry. So this is how you go in and actually deal with the inputs and outputs of various codes. We have adapters to connect to lamps, for instance. So if you're interested in doing molecular dynamics, we can build lamps inputs and outputs, and then you can run them on your own. All right, so let's go back to the lesson. So the second thing we're going to focus on for this lesson is something called input sets. So input sets are a way in which we standardize the parameters we use for DFT. And in PyMatGen, we have a number of input sets that correspond to materials project default parameters. So this means if you run your calculation with one of these MP input sets, you actually get the same parameters that we use when we run for production. So how do you use one of these input sets? Let me put a few blank lines so I can just get some more space on the screen. All right, so now how do we start using these input sets? Well, if I already have the structure under struct, and so I want to make an input set for that. So we're going to do something slightly different so we can get the tab completion. I'm going to have to first import the correct module. And so if I say import pymatgen.io.vasp.sets this time, hold down Shift, press Enter. Then I can type in pymatgen.io.vasp.sets, a final dot, and press Tab. And now you'll see a lot of different possibilities. And in fact, if you scroll down enough, you'll see some things that start with MIT and something that starts with MP. These are our input sets. Now, basically, the MP input sets are default parameters for a calculation that we might run in the materials project. They have a number of names after them, such as MD set, metal relax set, NMR set, SOC or spin orbit coupling, relax. These all correspond to different types of calculations that we have generated standard parameters for. And when we want to compute that, for instance, if we want to compute the NMR parameters for silicon in an inorganic material, such as a zeolite, we would use this set. So for the purpose of this example, let's pretend we just want to take our aluminum chromium structure and we want to basically optimize it. So we want to do something called a relaxation. So for the purpose of this example, we're going to want this MP relax set. So I click on that, it auto completes in. I'm actually going to go to the beginning of this cell and type from space, and then I'm going to delete that dot, put a space, and say import. So now your command looks like from pymatgen.io.vasp.sets, import MP relax set. If I hold down Shift and press Enter, I run that cell, and now I can use that set. So let's do relax underscore set is equal to MP relax set. And then if I hold down Shift and press Tab, I will get the introspection again, and I can see that it takes primarily one argument, which is the structure. So in order to generate all the parameters for this calculation, you really only need to give it the structure. So this is the first set of guardrails. If you have some structure you want to compute, you put it into this MP relax set and it figures out most of the other parameters you need. So let's say structure is equal to struct, which is what we named our aluminum chromium structure. I shift run this, and it'll basically process, and now I have a relax set. Let's say print relax set dot, and I'm going to press tab here to do auto completion. And I know that actually one of the attributes in this is this thing called an incar, which is the input parameters for VASP. So if I click on that, it'll auto-complete for me. I can do Shift Enter to run this cell. And you can see that it's printed out something that has a number of keywords in all capitals with an equal and then some property. So these are VASP input properties, and it's already computed a number of them. So it's figured out the EDIF, or the energy cutoff, that it wants to optimize to. It's figured out some default magnetic moments to run everything in. So the relax set starts off by running everything in a ferromagnetic configuration, which is the simplest magnetic configuration for symmetry purposes. It sets the accuracy, it sets the number of spin channels that are possible. So if you're going to do a spin polarized calculation. So these are the default parameters that we run in Materials Project. You'll also note that there's a bad input set warning. Basically, there are some very crude checks within the relax set to see if this is potentially a metallic system. And in this case, the aluminum chromium, it probably is a metallic system. And what it's saying is that this relax set might not be ideal for a metallic system. So you may want to use a different relax set. We have the MP metal relax set for that instead. What if we want a different type of calculation? Let's assume we actually say we saw this warning and we want to do that instead. Let's go find that MP metal relax set and actually try that out. So again, I'm going to say from pymatgen.io.vasp.sets import MP metal relax set. Let's actually try something. Let's see if I press tab here or shift tab. No, it's still not doing autocomplete for me, so I'm going to have to just type this in still. So it's MP metal relax set. I do shift enter, and now that's imported in. And I can say metal relax set is equal to MP metal. I'll just type in the MET and press tab to get my autocomplete to finish off the rest of that. Open up the parentheses and give it my structure. So I'll say structure is equal to struct. And in the same line, I'm going to say print metal underscore relax underscore set dot incom. And if I do a shift enter, you can see that it runs through. If we go up to this warning, it said something about I smear, which is one of the parameters. In this case, in the normal relax set, it's set to -5. If we go to the metal relax set, it's set to 1. And this is where understanding how DFT works is actually important to get the most out of these calculations, because this is a nuance of how DFT computes electronic structure for metals versus semiconductors and insulators. It's something called the smearing method for the computation. So at this point, I think it's best if we work on the exercise. So let's move over to the exercise. In this case, we're going to do the same thing as we said before. We're going to take what we learned for input sets with VASP and compute, or basically build an input set with Q-Chem. So again, we're going to work with this ethylene carbonate example. I have this ethylene carbonate molecule. I'm going to do shift enter on it. And it basically says I have this molecule. And what I would like to do is figure out the input set to use to compute an optimized geometry with Q-Chem. And in your example, I'm going to suggest you click on this code cell and you press A twice to get 2 more cells. And you actually start by importing that sets module. So you're going to say import pymatgen.io.qchem.sets. Hold down shift, press enter, and then type in pymatgen.io.qchem.sets, put a dot, press tab, get your autocomplete, and explore from there. So let's give ourselves about 2 minutes to go through this process. All right, so if you were able to get the tab complete working, which I understand a lot of people are having problems with that still, normally with Jupyter, if I just type in from a module import and then press tab, it will take some time, but it will basically give you the options of what you can import. it seems for some instance in CoCalc, we have to import that module first. And so that's why I gave myself 2 extra lines, one to do import pymatchen.io.qchem.sets. And then in the next line, I type in that module. So I type pymatchen.io.qchem.sets, and I have to put a trailing dot. And basically at this point, if I press tab, I get all of the autocomplete options for things that are available within this Q-Chem sets module. And you can see that I have basically that QC input that I saw before, but I also have a freq set, opt set, and a single point set. So these correspond to an optimization, a frequency calculation, and a single point, or basically just a static energy calculation. For the example, I want this opt set. So I'm going to click on that so it gives me my space back on the screen. And I'm going to basically type in this little underscore blank empty line here, opt set. So OPT, SET, opt set, shift enter to run it, and now I imported that. And again, I know that that's the set that I want. So OPT, SET, shift enter, and you can see that it basically converts the XYZ molecule that we had here before into a different kind of input that Q-Chem takes, right? After that, it has a section that basically has the various inputs for Q-Chem. So it has the job type, it has the basis, which is important for computing DFT, and a number of other parameters. Well, what if we didn't want to actually do this? What if we wanted to compute the frequencies instead? So in the next example, we would like to, or the next exercise, we would like you to figure out how to compute the frequencies. As I mentioned, there is that frequency set. So what do I put in this import? Plug that in here, run it, and look at what frequency set looks like. I'll give everyone a minute to go through this process. All right, let's run through this exercise very quickly. So again, I'm going to click on, actually, I have from before the imports that I've seen before, and I know what the set is called. So I'm going to click in this blank spot and type in FERQ, frequency set or freq set, shift enter, it will import that set. And so I can type that again in the next line. So FERQ set, shift enter, and let's take a look at what changed. We can see up on the optimized set, it says job type is equal to opt. And we can see down here, it says job type is equal to freq, which basically means that the calculation is very similar to the previous one. It's just running slightly different parameters, right? So let's take a quick look at what the inputs for freq set are, and actually examine what the inputs, the initialization arguments are. And I made a slight snafu here in this exercise example. I actually want help of the freq set class, not my object. That has the init, which is basically the method that gets run when I make a new frequency set. So if I do shift enter on this, it says that there is a molecule, there's a DFT rung, which is default set to 3. There's a basis set, there's a PCM, there's a number of parameters that affect the type of calculation that I want. So even though this computes a frequency, you can actually play with those parameters. So if I scroll down the bottom here, I already know what's going to go into this blank line. It's that same freq set, so FREQ set. And in this case, I'm actually going to run it with a different DFT rung. And the idea is that the higher the DFT rung, the higher the accuracy of the calculation, but usually the exponentially more costly in terms of compute time. So if I do a shift enter on this, you can see that the molecule is printed in the same way. We have a frequency again, right? But if you look down at the bottom, there's this method line that says B3LYP. If I scroll up, you'll see that in my normal rung 3 calculation, the method says WB97XD. Now, if you don't understand what's going on here, it's because the DFT rung is actually rather important for the calculation parameters. And again, even though you can compute, you can build these input sets, you can write the inputs, and you can run the calculation, if you really want to get the most out of this process, you should eventually learn what the DFT aspects are. But what the automation lets you do is to begin running calculations and get a hands-on feel for how DFT works. So we're going to move on to the next lesson. And this lesson might end up being mostly demo simply because it is actually decently long and it has a little bit of a complication in it. So if you can follow along, please go ahead. There is no exercise in here. It's just keeping up with what I'm typing in. Now, for the purpose of this lesson, we actually need to do one extra thing within the CoCalc system, which is to tell basically PyMatGen where the pot cars are, the pseudopotentials are. Normally this within our normal ecosystem on Binder and other online Jupyter examples, the pre-setup for the image works properly and this works out fine. For some reason, this isn't quite working right now in CoCalc, even though it worked before. So I'm going to walk you through what this looks like. I'm also going to put this line in Slack so you can copy paste it if you want to. I'm going to use an exclamation mark to run a terminal command. I'm going to say pmg config. I'm going to use a -- add, and I'm going to add a variable called pmg VASP PSP dir in all caps. So it's pmg underscore VASP underscore PSP underscore dir in all caps. And I'm going to give it a directory. So I'm going to say /home /user /python underscore module /mp underscore workshop /potcars in all caps except for the S. So POTCAR in caps, then S. I'm going to shift enter, run this, and I'm going to copy this and put this in Slack for everyone as well. So normally this is a configuration you only do once on your system. And for this purpose, this sets up PyMatGen, tells it where the pseudopotentials are. For this example, we're going to import the silicon structure. So I'm going to say SI, oops, no caps lock. SI is equal to structure.from file, and I'm going to import a silicon sif, which is called si.sif. Oh, that's right. If I have, for some reason, CIF in all caps, in Python, when reading files, it is case sensitive, so I have to have that there. Now, the next thing we're going to do is talk about workflows. And this is a pretty big jump because I haven't talked to you about anything else in between in terms of how you manage workflows. And this is kind of the point. The way that Automate, which is our workflow recipe code, works is you don't have to worry about anything as long as you have fireworks set up properly. And even though that is not an easy process, it is a very system-specific process, so it's not really appropriate for this workshop. If you have, there is a tutorial on the Fireworks Workflow Manager website that you can go through, and there's a tutorial on the Automate website for how to set up Fireworks, but this is really a system-specific process, so you can always reach out via the MathSci discussion forum that we talked about if you're having trouble with that. So I'm going to first say from automate.vasp.workflows import, and I'm going to import a workflow that I know about called the structure optimization workflow. So I'm going to say wf underscore structure underscore optimization, and I'm going to run this. And what this workflow does is build a firework, which is what we call a job, with the right set of inputs so that we can insert it into our database and have it just run for us. So if I say wf is equal to wf underscore structure, I'll use tab completion to finish off the underscore optimization, open a parentheses and say structure is equal to si. In that same cell, I'm going to enter a new line and say print wf. And you can see that it's created a workflow object, which doesn't really tell us much. It has something called an FWIDs dictionary, which has one thing and has a name of silicon. So let's do something slightly different from the lesson. We're going to just show you what happens in terms of putting this into the database. So if you were here in the Python primer, you also went through MongoDB. We use MongoDB to store our workflows and to store our calculation data. So if I do wf dot as underscore dict and do shift enter, you're going to get a rather long print output. This is a dictionary version of this entire workflow. So it has an FWS key, it has fireworks built into it. So each firework is a job, and you can see that there is a structure. It says it comes from a PyMatGen core structure object. It has a lattice. It has all of those sites that are part of the silicon system. It also has an input set, so it has a certain set of input parameters associated with it. In this case, it's the MP relax set and the structure that's going to be used when we compute that input set. And it has other parameters such as what the VASP command is, some extra potential parameters to tweak this one calculation, and other steps that will basically run VASP and then put this into the database. So this entire job will take care of setting up the input, running VASP, correcting for any errors on the fly, and putting the output of that calculation back into the database so we never have to touch VASP in the process of running this workflow. But, that's all great and dandy. So if I can put this into my Fireworks system, it should run within Fireworks and give me an output where I don't have to actually understand how to run VASP. But what if we wanted something more complex? What if we wanted to compute the electronic structure for a system? Now, that can be a lot more difficult. It usually takes a number of calculations. Is there a workflow already for that? So I type in from atomate.vasp.workflows import wf_band structure. And I'm going to shift enter to import that. I'm going to say wf is equal to wf_band structure. And I'm going to give it, as for the structure parameter property or the argument, the silicon structure. So now let's do print on this. So I say print wf. And you can see that there's actually a number of new keys within this FWIDs, -2, -3, -4, -5. Fireworks in this situation gives it negative IDs because it's not associated with a database. But let's see what this actually looks like. And so in order to do this, we're going to import a helper method for this workshop. So I'm going to say from mp_workshop.atomate import wf_2_graph. I'm going to shift enter. I'm going to say wf_2_graph wf. And so now this is a picture of what this this workflow actually looks like. So there is a structure optimization job that begins. It automatically will feed its data into what's called a static calculation, where we basically compute for this optimized geometry a better quality calculation of the energy, the charge density, and the wave functions. We then feed that into two calculations that basically go through the reciprocal space of the Brillouin zone and calculate critical K points, either via a uniform mesh or along very special high symmetry lines that which is what you see when you look at a band structure on the materials project. So this is exactly what we would compute if we were computing silicon. I'm going to give everyone a minute. I'm going to check Slack to see how everyone's doing and see if there are any issues. So I've seen a number of questions regarding workflows for various things. So I'm going to go through and show you some of the different workflows that are available. So if I basically import this workflows module here, we can start going through it and look at what's available. So I'm going to say from atomate.vasp.workflows import, or actually, let's delete that. Let's just import that module so we get autocomplete. I'm going to say import atomate.vasp.workflows, shift enter, and I'm going to give myself a couple blank lines so that I can move this into the center of the screen. And now I'm going to autocomplete on the workflows module to see what's available. Let's say atomate.vasp.workflows press tab. And there are a number of things that are available automatically. Most of these initially are not things that you want to focus on. If I scroll all the way down to wf_, these are preset workflows. And you can see that there's a number of calculations that are available. You can compute traditional band structures. You can do a band structure without optimization. There is a post-processing calculation called bootstrap, which computes effective masses from the band structure. There's a higher order calculation called an HFC calculation. You can compute the bulk modulus. You can compute dielectric constants, elastic constants. So this is the full elastic tensor, the Gibbs free energy equation of state, the NMR, the silicon chemical shielding NMR tensors. You can run a nudge elastic band calculation, which helps you compute a diffusion barrier for moving an atom from one site to another site. a piezoelectric constant, again, this is the full piezoelectric tensor, the Raman spectra for a material, and then the static and structure optimizations calculations, as well as one to compute the thermal expansion from the equation of states. So these are all workflows that we have developed. We have benchmarked against experimental data. We have then gone ahead and written a paper, built validation process, and then basically evaluated the error of the DFT process versus experiments, optimize those parameters so that we're within a tolerable error. For example, for the elastic constant workflow, our calculations are within 15% error of the experiments. And if you look at the variability in the experimental values, that's about 15% as well. So we're within experimental error for most of these calculation types for these properties. So this is also the set of workflows that we run to compute anything on the materials project. So if you are looking, for instance, at a new system and you're computing formation energies, if you use these workflows, you will actually have calculations that are 100% compatible with what we're computing. And so you can mix the energies of our phase diagrams and the phase diagrams that you compute. So let's move on, and I'm going to show you basically a demonstration of how you can run a workflow. Now, we don't have VASP in this CoCalc environment, so we've actually developed something where we can pretend to run VASP. So I'm going to say from mp_workshop.animate import use_fake_VASP_workshop. So this is a little helper utility we built so that you can pretend to run VASP. And the next thing I need to do is import something called the launchpad from Fireworks. So I have to insert this workflow into my database. And the way I do that is the launchpad in Fireworks is kind of a wrapper of my database that makes it easier to work with and that I don't have to know Mongo queries at this point in time. So I'm going to say from Fireworks, import launchpad, and it's a capital P on the pad. And then I'm going to run the next cell, LP is equal to launchpad.auto_load. And this will just pull the launchpad or the database properties or the credentials from the environment. Now, if you have a new Fireworks database, there's something you do at the beginning to just set it up or clear those collections to make sure you're starting with a nice clean setup. You usually only do this once, so I don't recommend you do this without knowing exactly what you're doing. And that's resetting the launchpad. So if you have 10 Fireworks in your database already, after you've gone back and you've set up Fireworks on your system, please don't reset the launchpad unnecessarily. This is only for this example. So I'm going to say lp.reset. I'm going to say password equals none. And I'm going to say require_password equals false. And this will just let me forcibly reset the launchpad. So it said it's basically reset the launchpad. And now I can go ahead and add a workflow in. So let's go back to the workflow that we had before. And I'm going to use my little helper function, use fake VASP workshop, so that it uses fake VASP instead of trying to launch a real VASP calculation. So I'm going to say workshop_WF is equal to use fake, and then press tab to autocomplete and give it my band structure workflow. Let me add a few more lines. So this will go to the top of the screen. And now I can say lp.add_WF, and I'm going to give it the workshop_workflow. And so it's told me that it's added a new workflow into the Launchpad, which is my database of workflows to run. It's remapped some of those Firework IDs to 1, 2, 3, 4. So I have 4 calculations that are waiting to run. So the next question becomes, how do I figure out what's going on? Well, I'm going to say LP dot, I'm going to press tab to get my autocomplete, which might take a minute. Or it doesn't run on CoCalc. There we go. And there are a number of methods that I can use directly on this. I'm going to type in get, and I'm actually going to look for something that gives me information about the whole workflow. And I'm going to say, oh, I see something that says get WF summary dict. So I'm going to click on that to autocomplete it. And I know from this, from previously working with fireworks, that I can access any workflow by the individual firework IDs. So I can give it 1, 2, 3, or 4, and it will find the corresponding workflow. If I hold down Shift and press Tab, I get the introspection, and it tells me I need to give it a firework ID. So any of the fireworks in this workflow I can reference. So I'm going to put in 2 for the purpose of just playing around with this and do Shift Enter. And I'll close this introspection. Oh, there we go. So let's look at what this workflow. Its state is ready. Its name is silicon. It has a created on and an updated on, which were today. And it has basically 4 different calculations: the structure optimization, the static, the uniform NSCF, and the NSCF line. You'll notice these 3 say waiting, because if we look up at this graph, we have to first run the structure optimization and feed data into the next calculation. So these are actually waiting for the structure optimization to complete. So these 3 fireworks or jobs here are waiting for something else to complete, and the structure optimization is ready to run. So this is the one that's going to run first, right? So how do we normally run this? Well, we have 2 options. We can run this in the Python notebook as an object, which is not normally how we would run a calculation. Normally what we would do is use a command called qlaunch to submit the calculations to our supercomputer. They would run on the supercomputer. It would basically take care of everything associated with that. And we would then be able to see the documents that summarize the calculation in our database. You can manually run a firework or a job, if you would like, using a command called the rlaunch. So I'm going to do an exclamation, because this is normally a terminal command, and type in rlaunch and type in --help. And so if I scroll up a little bit, it says, okay, to use this, we can give it a number of different parameters. This program launches 1 or more rockets. A rocket retrieves a job from the central database, runs it, and then basically completes. And so I can run it in a single shot mode or a rapid fire mode. And I'm going to, for the purpose of this example, just run it in rapid fire mode, but have it run just 1 calculation. So I'm going to say exclamation mark rlaunch, rapid fire. I'm going to do --n launches. I'm going to enter 1 and do a Shift Enter. So this is the command the supercomputer would run in the job that it has. So it will go on the supercomputer. Fireworks will basically, if I scroll up, it will first figure out where it is, connect to the database. It creates a new directory. It will grab a firework or a job and it'll run each step. So it'll write the outputs. In this case, it's writing the VASP outputs from the IO set. It will run VASP, and because of our helper, it's going to run something called fake VASP. It's going to then pass those calculations to the next firework, and then basically take all of those files, build a summary dictionary that it puts into the database. And then we can access those database files if we want to. So I'm going to click on this files directory, and I can see that there's a new folder in my exercise, in my 05 automated DFT called Launcher 2020. This is basically an example. You'll notice that the name of the folder is just a timestamp, and this is just a way to produce a unique folder. We, in Materials Project, focus on the database as our way of differentiating calculations, and so we just need some unique name for the folder. If you've done computational materials science before, you probably named this the name of your calculation. And while that's very good for going through your data from folders and files, when you switch to a database, you no longer worry about the name of this folder. You really want to start working with a database if you're going to start running hundreds, thousands, or tens of thousands of calculations. Otherwise, the number of calculations becomes unmanageable. So if I click on this launcher, I will see there's a number of files already in here. There's the in-car, K-points, potcar, and poscar file. So these are the inputs. The calculation ran 2 steps, actually, the job. It ran an initial relax 1, so it runs the structure optimization once. It takes the output structure and reruns it again to make sure there's no extra stresses in the lattice. So this actually ran 2 VASP calculations using our fake VASP, but the actual calculation runs VASP twice, even though it's a single job. And the outputs of all of this are put into the database. There are also a number of other files that are generated. So for example, there's these charge car files, which represent the charge density. These are volumetric. You can choose to put this in the database if you want, and then you can access them later on. So you can grab all of the calculation details directly from the database, and you don't actually need to go into this folder. What we do in Materials Project is we save the folder and we archive it into cold storage. Basically, there might be a day in the future where our database gets destroyed, and what we are able to do at that point is come back to these folders, open them back up, run the code that basically converts this folder into a document and puts it into the database, and we can restore all of MP that way. So in that way, we're resilient. Even though we rely on the database to do all of our processing, we can rebuild a database from scratch as long as we have all the raw calculations. And so this, we find, is a much better way to think about high throughput and run large numbers of calculations and do data science rather than trying to do individual calculation management.